Today, we're focusing on the Data Center MVAC system, specifically the advanced concepts in Module 10. We'll dive into key components like CRAH units, fan walls, CRAC DX, make up air, dehumidifiers, and containment. The main goal here is to control airflow, temperature, humidity, and containment in a way that ensures the IT equipment's inlet air meets requirements, not just the average conditions of the room. This approach is essential for maintaining performance and reliability in data centers. Understanding how each of these systems work together is critical for effective environmental control. This module focuses on Hall Airside Cooling and its critical role in maintaining optimal conditions for IT equipment. The primary goal is to protect rack inlet conditions by carefully coordinating heat removal, airflow management, moisture control, system resilience, and providing evidence of performance. Starting with thermal duty, we need to efficiently remove the IT-sensible heat at the specified inlet and water or refrigerant conditions, while differentiating between installed, available, and net sensible capacity. For the air path, it's essential to deliver airflow directly to the IT intakes, with controlled bypass and recirculation, ensuring proper containment, floor or plenum conditions, and fan operating points are verified. Moisture duty involves assigning a single dew point authority to the makeup air unit, dedicated outdoor air system, or dehumidifier, while keeping the computer room air handler and fan wall units mainly handling sensible heat. Lastly, resilience and proof require mapping maintenance and fault scenarios to the target system topology and demonstrating that the system performs reliably under typical load and failure conditions. The outcome is an airside cooling system that stays thermally stable, maintainable, and demonstrably compliant with all performance requirements. This module focuses on Hall Airside Cooling within the Data Center MVAC system. Here, we evaluate several critical factors together: safety, thermal continuity, maintainability, efficiency, and evidence. Starting with safety, we consider fire and smoke interlocks along with refrigerant safety measures. Leak containment, condensate management, and safe access are crucial, and importantly, no operational sequence can override life safety controls. Next, continuity ensures a stable rack inlet environment during transfers and restarts, with capacity and distribution paths aligned to resilience goals, and the system includes autonomous local fallback if networks fail. Maintainability involves safely isolating components like filters, fans, coils, valves, and circuits while preserving service clearances and access paths. Every return to service must be backed by verified evidence. Finally, the key decision rule is that any low-energy solution can only be accepted if it maintains the required thermal stability and resilience, ensuring system performance and safety are never compromised. This module, titled Hall Airside Cooling, is part of our advanced training on data center MVAC systems. It follows a structured learning route, moving from design intent all the way to operating proof. We begin with the design intent, focusing on critical boundaries like heat, airflow, moisture, and pressure, as well as equipment duty, redundancy, and how everything interfaces. Next, we dive into calculations, covering airflow, coil duty, water flow, and equipment counts, along with moisture removal and pressure makeup. Then we explore architecture, including components like CRAH, FWU, CRAC DX, MUDX, and dehumidifiers, plus containment strategies and control authority. Controls come next, examining different operating states, alarms, interlocks, and fallback procedures. For testing, we look at evidence from factory to integrated tests, including failure injection and recovery scenarios. Finally, operations focus on troubleshooting, maintenance, emergency procedures, and ensuring readiness through trend monitoring and handover protocols. This comprehensive sequence mirrors how design, construction, commissioning, and operations teams work together effectively. In this module, we focus on Hall Airside Cooling, a critical component of data center MVAC systems. By the end, you'll be able to design, test, and operate every family of airside cooling solutions effectively. We start with design competence, where you'll learn to define key parameters like rack inlet conditions, airflow, dew point, and pressure criteria. This helps you select architectures based on actual physical requirements, not just equipment preferences. You will also map tier and rated objectives into maintainable systems that can respond to faults efficiently. Moving into calculation competence, you'll master how to calculate sensible airflow and water flow, correctly size your cooling units, and manage outside air latent loads along with fan failure compensations. Commissioning competence teaches building evidence from level 1 to level 5 and verifying system responses for alarms, interlocks, transfers, and recovery scenarios. Finally, operating competence guides you in identifying thermal imbalances accurately and restoring safe conditions by analyzing real-time measurements of airflow, temperature, pressure, and moisture. The overall training standard emphasizes understanding the physical causes, quantifying cooling duties, verifying system responses, and keeping solid evidence throughout. This module focuses on data hall airside cooling within mission-critical data centers. We'll cover a practical design-to-evidence approach, starting with the system and boundary conditions, including the thermal and air paths and the roles of key components like CRAH, FWU, CRAC, MAU, and dehumidifiers. We'll also look at how these systems interface with chilled water, refrigerant lines, power, building management systems, and fire alarms. Next, we'll dive into sizing and selection, examining heat balance, airflow, coil, and water duty, along with considerations for capacity margin, redundancy, growth, and maintainability. Then, we'll explore controls and failure modes, including control sequences, alarms, authority and fallback procedures, and how the system responds to sensor, fan, coil, or path failures. Finally, we'll discuss commissioning and operations, covering various levels of evidence and integrated testing, acceptance criteria, troubleshooting, maintenance, standard operating procedures, and handover. Throughout the module, 5 detailed calculations are integrated across critical equipment sections to provide practical, real-world insight. Now, let's focus on selecting the appropriate airside cooling system for the data hall. The key is to start from the physical cooling duty, ensuring that the system matches the heat density, air path, moisture control, topology, and service access requirements. For example, chilled water CRAH units are ideal for room or row cooling with sensible coil duty, while modular fan wall units offer large fan capacity with zonal air delivery. DX CRAC units provide self-contained direct expansion cooling with local heat rejection, and make-up air units or dedicated outside air systems handle outside air with pressure and moisture control. Dehumidifiers assist with latent load management and dew point control. The design principle here is to separate sensible cooling, ventilation and pressurization, and latent duties, then integrate everything through a single thermal state model to ensure efficient and reliable performance. This coordination is vital for effective data center cooling. In this module, we focus on data hall airside cooling and the crucial concept of system boundary and interface ownership. Every interface in the data center cooling system must have a clearly designated owner along with defined signals, acceptance criteria, and restoration rules. For example, on the electrical side, we manage normal and standby power, including UPS controls. On the air and room side, aspects like containment and rack inlet conditions are controlled. Cooling units like CRAH, FWU, and DX have their own net duty responsibilities. Plant and ambient factors cover chilled water, condenser operations, and weather derates. Finally, control and fire systems include building management systems and life safety protocols. This interface register ensures accountability for power sources, isolation, control authority, sensing, alarms, safe states, resets, and proofs for returning to service. Understanding and managing these interfaces is key to reliable and efficient cooling operation in the data hall. In this module, we focus on identifying all the equipment and physical boundaries involved in data hall airside cooling. It's crucial that real equipment is only accepted when its accessories, maintenance paths, and command and feedback chains are fully complete. Starting with the air boundary, it includes the filter, coil, fan, and supply path. Here, we measure filter differential pressure, air temperatures, and the fan's operating state to ensure proper function. For the water or refrigerant side, key components are isolation valves, strainers, drains, vents, and the refrigerant circuit itself. The important checks involve proving flow, monitoring temperature, and ensuring leak safety. Control and service aspects include local controllers, the building management system, leak detection, and fallback mechanisms, all while maintaining safe access and clear replacement paths. Remember, field verification shows that accessories are integral parts of the system's duty and not just optional additions. This module covers data hall airside cooling in detail, focusing on the key design criteria that must be established before system selection. First, a credible calculation depends on starting with controlled inputs and setting measurable acceptance values. We look at load and duty, including IT sensible heat per hall or zone, plus allowances for lighting, people, and building envelope. It's crucial to account for present, future, and test loads to ensure flexibility. For air and environment, we define rack inlet classes, project set points, supply and return temperatures, and allowable transients, along with containment leakage and pressure targets to maintain stability. Water and refrigerant considerations include chilled water supply and return temperatures, coil approaches, ambient design conditions, and equipment derating, alongside refrigerant safety classifications and charge controls. Resilience focuses on the target tier level or rated objective, plus maintenance and fault cases, power transfer strategies, and restart philosophy to ensure continuous operation. Controls cover sensors, authority levels, fallback modes, and operation during network outages, including alarm management, reset procedures, and restoration permissions. Finally, evidence involves declared vendor rating conditions, the accuracy of factory and site instruments, plus trend intervals, load steps, and acceptance margins, all ensuring the system meets design expectations. Here, we're looking at the complete architecture of Data Hall Airside Cooling, which involves closely tracking heat, air, water, moisture, power, and evidence. The key idea is that the system is truly complete only when every physical stream and control dependency comes full circle. Starting with the IT load, we monitor the rack inlets and heat exhaust to understand the thermal demands. Then, in containment, separate air streams are maintained to limit bypass airflow, ensuring efficient cooling. The air unit combines fans and coils to deliver the net cooling capacity needed. On the heat rejection side, chilled water plants or direct expansion systems handle the heat load, but their performance can be affected by ambient conditions, so derating is considered. Control and proof come from building management systems and control points that monitor meters and trends. The control boundary is critically defined. Rack sensors directly influence thermal demand. The makeup air unit manages moisture levels, and life safety systems retain ultimate authority to override controls if necessary. This integrated approach ensures efficient, reliable data hall cooling. In this module, we're focusing on Data Hall Airside Cooling, specifically the sizing inputs and verification checklist for the MVAC system. It's crucial to freeze all your inputs before selecting equipment, making sure you separate the margin from redundancy for accurate planning. Inputs include the IT load density and diversity by zone, rack airflow, and supply and return temperatures, along with the type of containment used. We also consider cooling water temperatures or direct expansion conditions, as well as outside air, leakage, exhaust, and dew point design conditions. Planning must account for future fit-out, maintenance, and failure scenarios. Moving on to boundary conditions, we look at rack inlet class and project set point bands, plus available electrical and hydronic paths in various operational states. Equipment vendor capacities must be declared based on actual entering conditions. Don't forget to factor in service access, safe isolation protocols, fire and smoke actions, test loads, sensor mapping, and the uncertainty that comes with these elements, all tied to clear pass or fail criteria. Always remember, the most important factor in selecting equipment is the worst credible operating state, not just the nominal point listed in the catalog. This ensures your system is robust and reliable under all foreseeable conditions. In this module, we're diving into Data Hall Airside Cooling with a focus on key engineering formulas. We use one coherent model that integrates heat, airflow, moisture, pressure, and redundancy for accurate system analysis. Starting with airside heat, represented by the formula Q sub S equals air density times specific heat capacity times airflow volume times the temperature difference. Keeping units consistent is crucial here. On the water side, heat transfer is calculated by multiplying the water mass flow rate by its specific heat and the water temperature difference, and make sure to use measured water density when converting flow rates. Airflow balance must account for supply, IT load, bypass, and recirculation air volumes to ensure the field map closes within allowed uncertainty. For moisture removal, the key is using the humidity-ratio difference rather than just relative humidity. Pressure leakage involves calculating airflow based on discharge coefficients, equivalent area, and pressure differentials, adding allowances for exhaust and doors. The fan laws tell us that airflow, pressure, and power scale with fan speed in different ways, which is essential when validating motor and noise margins after a fan failure. The bypass fraction measures unused supply air, and that unused air wastes energy without cooling the IT equipment. Lastly, equipment count is determined by taking the ceiling of the maximum duty relative to unit capacity, and redundancy is added only after this count is fixed. This comprehensive approach helps us ensure efficient and reliable cooling performance in data centers. Here we walk through a worked example to determine the hall airflow and the number of CRAH units needed for cooling. We start with our design sensible load, which combines the IT load of 4 megawatts with an additional sensible margin of 0.2 megawatts, totaling 4.2 megawatts. Using this load and the temperature difference of 12 Kelvin, we calculate the required airflow, which comes out to just over 1 million cubic meters per hour. Next, we figure out the number of CRAH units needed by comparing the load per unit and the airflow capacity per unit. The higher of these two values is 21, giving us the baseline CRAH count. Hydronic duty is then calculated to find the water flow needed overall and per CRAH unit, ensuring proper heat removal. Finally, we select 21 units plus 2 spares for resilience, making sure the system can handle the load even if 2 units are unavailable. Throughout, we check all calculations against system performance criteria to ensure accuracy and reliability. On this slide, we're diving into the key concepts of design margin and redundancy within Data Hall Airside Cooling systems. It's important to understand that design margin and redundancy are different quantities, and we must always keep both visible to avoid double counting or hiding capacity. Starting with duty or demand, this refers to the coincident design heat and airflow, which includes only justified non-IT loads. It's based on the actual rack inlet and plant or ambient conditions. This is the core workload the system must handle. Next, design margin covers the uncertainties such as measurement degradation and approved future growth. Think of it as a transparent percentage or explicit future load, but importantly, it's not a replacement for true redundant capacity. Speaking of redundancy, this is the capacity or path available during maintenance or in a fault situation. It comes from the target topology and failure analysis, and must be clearly demonstrable through switching and load tests. Finally, a key acceptance rule is to clearly state whether each installed unit serves as duty, margin, redundant capacity, or future fit-out reserve. This clarity ensures proper system design and reliable operation. This slide outlines the control state sequence for Data Hall Airside Cooling, focusing on load, humidity, failure, and restoration. The key point here is that the room operates as a distributed system, where the central CPOS or BMS coordinates overall control, but local units maintain protective autonomy to respond quickly to their environment. Starting with the normal state, we modulate fans, valves, or compressors to meet rack inlet demand while maintaining pressure and dew point through the makeup air unit or dedicated outdoor air system. When there's a load rise, we increase capacity, verify the air path, and ensure there's enough plant and electrical margin before activating standby units. In a low-power scenario, controls maintain essential airflow according to the approved ride-through design, while a thermal timer track system trends to manage the transient. During restoration, fans, valves, pumps, and compressors are sequenced carefully to prevent sudden inrush or abrupt changes in temperature or pressure. Finally, the system only returns to normal operation after confirming that rack inlet conditions, dew point, flow and pressure, alarms, and available capacity are all within safe parameters. The restoration requires permission based on a stable control source, available cooling paths, and physical room conditions within the approved envelope. This ensures safe, reliable recovery from any disruption. This slide covers the alarm philosophy for Data Hall Airside Cooling, which is vital for maintaining thermal margin before any shutdown occurs. Alarms are categorized and prioritized based on their physical impact, and each one comes with a clear, defined operator response. Starting with P1 alarms, these indicate an immediate thermal or safety risk, such as a high rack inlet temperature or issues like leaks or smoke interlocks. The response here is crucial. Start any available reserve capacity, isolate the fault, protect the IT equipment, and escalate the situation. P2 alarms signal reduced resilience, like fan or module failure, sensor disagreements, or dirty filters. While the system remains stable, the response is to verify fallback options, maintain margin, and plan for urgent fixes. P3 alarms relate to maintenance or efficiency concerns, such as rising pressure drops across filters or coils, airflow drift, or calibration needs. These require investigation before they start affecting thermal margins. Alarm quality is emphasized by setting strict parameters, including setpoint basis, delay, deadband, and reset rules, all designed to prevent nuisance alarms. Notably, safety and leak-related alarms do not auto-reset until the cause has been fully inspected and approved for return to service. This structured approach ensures reliable cooling and protects critical infrastructure. Here we see the instrumentation architecture used in Hall Airside Cooling, which is crucial for measuring the physical decision points in the system. Redundant sensors play a key role in protecting control continuity, ensuring that operations can continue smoothly even if one sensor fails. At the same time, independent reference instruments safeguard the quality of evidence, which is vital for trustworthy data analysis. The sensors are strategically placed across several key areas. At the rack inlet, monitoring top, middle, and bottom positions on representative racks. Within the airstream, measuring supply and return pressures along with filter differential pressure. On units and coils, tracking fan power and speed, valve position, flow, and temperature differential. And in the room and makeup air units, observing dew point, room differential pressure, and outside air conditions. Finally, calibrated reference instruments provide time-synchronized trends that serve as reliable evidence. By using both a distributed control sensor map and an independent commissioning map that records sensor location, accuracy, calibration, and uncertainty, we maintain a comprehensive and accurate view of the system's performance. This slide focuses on the critical role of containment in Hall Airside Cooling. Containment is essential because it separates different air streams, and any breach here can significantly impact the thermal margin. When containment isn't perfect, three main issues arise: bypass, recirculation, and leakage. Bypass occurs when the cold supply air avoids the IT equipment, causing fan power to increase without effectively cooling the racks. Recirculation or breaches happen when hot exhaust air re-enters the intake side, often due to open doors or missing blanking panels, which disrupts the cooling airflow. Leakage, on the other hand, alters pressure and airflow distribution, further complicating temperature control. The intended airflow path is straightforward. Cold supply air moves through the IT equipment intake, is heated by the racks, and then returns through the contained exhaust. To ensure this system works correctly in the field, we rely on tools like airflow maps, pressure monitoring, door and seal inspections, rack inlet temperature measurements, and calculating bypass fractions. These together help us maintain efficient cooling and preserve the thermal margin. In this module, we focus on the airside cooling in the data hall, specifically how the CRAH unit operates. The key principle here is that heat from the air passes across the coil into the chilled water, effectively removing it from the data hall environment. It's crucial to keep the coil predominantly sensible, meaning we avoid moisture removal and ensure proper containment. This helps guarantee that the cooling capacity actually reaches the IT equipment inlets. On the air side, the airflow path follows return air moving through a filter, then across the coil, followed by an electronically commutated fan, before being supplied back to the data hall. The sensible heat transfer on the air side can be calculated using the formula involving air density, specific heat, airflow rate, and temperature difference. On the water side, chilled water flows through a control valve or PICV, passes the coil, and exits as returning water. The heat transfer here depends on the mass flow rate of water, its specific heat, and the temperature difference between entering and leaving water. Another critical aspect is condensate management. If the coil surface temperature drops below the dew point of the entering air, moisture will condense. Therefore, proper condensate pan, trap, drain, and leak detection systems must be in place to prevent water damage. Finally, acceptance proof involves verifying several factors: balancing the air and water side heat transfer, checking rack inlet temperature distribution, ensuring the coil temperature approach is correct, confirming fan operating points, monitoring filter differential pressure, assessing valve response, and ensuring condensate safety systems are fully functional. These steps ensure the airside cooling system performs efficiently and reliably. This module covers Data Hall Airside Cooling, focusing on CRAH selection based on declared net performance rather than catalog nominal capacity. The selection process integrates capacity, airflow, hydronic, electrical, controls, and maintainability criteria to ensure comprehensive system optimization. Starting with thermal and airflow considerations, we evaluate net sensible capacity at actual entering air and chilled water temperatures, factoring in airflow and external static pressure under dirty filter and containment conditions, while consistently including fan heat in the net duty calculation. For the fan array, a modular EC fan arrangement is specified with defined loss of fan performance. It is crucial to verify the motor speed, power, and acoustic headroom after making compensation adjustments. Additionally, service access should be designed to avoid exposing moving parts or causing airflow collapse. In hydronics, attention is given to coil pressure drop, PICV and PICCV authority, strainers, isolation valves, vents, and drains. Measured flow and temperature differential support heat balance verification. Note that automatic leak isolation is a risk control feature for the project, not a generic tier requirement. Regarding power and controls, every power state must have declared behavior for controllers, actuators, and fan restarts. The system should include local fallback options to maintain operation if communication with BMS or CPOS is lost. Power quality targets are based on project specifications or IEEE standards, rather than a fixed TIA value. Finally, it is important to specify measurable response and acceptance criteria, avoiding the assignment of project-specific seconds or THD limits to uptime or TIA standards without a formal clause basis. This ensures clarity and aligns expectations in performance validation. In this module, we're focusing on the CRAH hydronic and control architecture for Data Hall Airside Cooling. The key components start with the valve, which controls the coil duty by regulating flow. The plant system maintains the available differential pressure to ensure consistent operation, while room sensors are strategically placed to protect the rack inlets from overheating. On the chilled water supply side, we have a riser with differential pressure availability and isolation capabilities. This is followed by strainers that are cleanable, along with flow meters and ports for accurate monitoring. We utilize PICV or PICCV devices to limit flow and provide modulating control to match the coil's cooling needs precisely. The CRAH coil itself is designed to maintain an optimal air-to-water temperature difference, incorporating pan and drain features to manage condensate effectively. On the return side, chilled water return temperature is monitored to maintain heat balance and overall system efficiency. The control sequence is essential. It starts with detecting rack inlet temperature demand, which then drives fan airflow adjustments, followed by valve or flow modulation, and finally coil heat transfer. A critical point to remember is to avoid simultaneous controls that could conflict or fight each other, ensuring smooth and efficient operation throughout the system. In this module, we focus on Data Hall Airside Cooling, specifically the CRAH ride-through and failure response as part of advanced MVAC training. For Tier 4 uptime, maintaining a stable environment through mechanical restart is crucial, but there's no one-size-fits-all restart time or UPS design. During power transfer, it's important to clearly define how controllers, actuators, and fans behave, utilizing ride-through, standby power, or thermal storage as needed, all tested under realistic heat loads. When fans or sensors fail, compensation must stay within verified limits, employing redundant sensor logic and starting reserve capacity before thermal margins run out. For coil or water leaks, moisture and flow abnormalities need prompt detection and isolation, with no auto reset until a physical check and drainage occur. If the control network is lost, the local controller should manage a safe autonomous sequence, avoiding reliance on a single master controller and ensuring manual operation can be restored. Ultimately, the goal is to keep rack inlet conditions stable throughout the entire verified restart interval and all fault scenarios. On this slide, we're focusing on the CRAH calculation for Data Hall Airside Cooling, covering airside and waterside parameters along with the installed quantity of units. Starting with the example assumptions, we have a design sensible heat load of 4.20 megawatts, an air temperature difference of 12 Kelvin, and a water temperature difference of 10 Kelvin. Each unit is rated at 200 kilowatts net and handles 53,000 cubic meters per hour of airflow. First, we calculate the required airflow by dividing the heat load by the product of air density, specific heat, and temperature difference, resulting in approximately 1,043,600 cubic meters per hour. Next, we determine the number of units needed based on capacity by dividing 4.2 megawatts by 200 kilowatts, which gives us 21 duty units. Checking airflow count, dividing the total airflow by unit airflow capacity yields 20 units. However, since capacity governs, we stick with 21 duty units. For water flow, we divide the heat load by the product of water's specific heat capacity and temperature difference, giving a total water flow of about 100.5 liters per second, or roughly 4.79 liters per second per unit. Finally, considering the project's N+2 redundancy criterion, 23 units should be installed, so that even if 2 units are unavailable, the system can still deliver the full 4.20 megawatts net capacity. It's crucial to verify all these calculations with vendor ratings under specified chilled water and air conditions, account for fan heat, filter condition, valve authority, and perform tests simulating 2-unit unavailability to ensure reliable performance. In this module, we focus on the Data Hall Airside Cooling System, specifically the fan wall unit or FWU. The core working principle here is that modular fans generate zonal airflow at a low pressure, which is crucial for efficient cooling. The fan wall acts as an air distribution system, where the coil arrangement, fan redundancy, and service isolation collectively define its overall resilience. When it comes to air delivery, we rely on low external static pressure, a large face area, and direct drive electronically commutated fans to ensure performance. It's important that the wall airflow matches the specific demand of the racks and maintains the containment pressure effectively. Fan modularity plays a key role. If one fan fails, it impacts the operating point of all remaining fans. That's why hot swapping is only safe when there's proper isolation and confirmed pressure stability. Regarding coil architecture, the setup, whether single, split, or interleaved coils, must be designed to meet the required path resilience. Separate A-B paths are only necessary when the full failure case involving valves, pipes, and coils is carefully engineered. Finally, acceptance proof is critical. This includes verifying wall airflow, fan operating points, coil duty, fan loss compensation, service isolation, and the rack inlet map, to ensure everything performs reliably under all conditions. In Module 10, we focus on Data Hall Airside Cooling and the critical considerations for selecting fan wall units, or FWUs. It's important to understand that modular redundancy isn't just a simple count of fans. It's a full system calculation. Multiple fans don't automatically give you N+1 capacity or ensure concurrent maintainability. When defining wall duty, you need to precisely determine the zonal heat and airflow at your selected supply and return temperatures, while accounting for pressure drops caused by plenums, coils, filters, grills, and containment. For the fan loss case, calculate how the remaining fans will perform in terms of speed and power using fan laws. You also need to verify that the motor, drive system, acoustics, and vibration have enough headroom. It's crucial to confirm airflow distribution across the whole system, not just the total volume. In the maintenance case, ensure there is guarded extraction, local isolation, and safe access for work. Test the pressure response when fans are removed and reinstalled. Also, keep your spare fan and drive strategy aligned with your restoration time goals. When dealing with hydronic paths, define whether your A and B coils operate on a 50-50 split, fully redundant 100-100, or staged duty. You must prove that pipes, valves, coils, and controls maintain independence within the boundary declared. Lastly, topology evidence must be path-specific. Fan modules, coil circuits, valves, piping, power, and controls all need to survive the same stated event, ensuring the system's resilience under failure conditions. On this slide, we focus on the FWU hydraulic paths and their role in managing capacity after a path loss. Documenting the remaining capacity is crucial so we can understand how the system performs under different scenarios. Interleaved coils help improve airflow distribution, but the overall resilience really depends on the rated capacity of each full A-B path. We have key components here, including CHWSA and CHWSB for chilled water isolation and PICV valves that regulate flow. The coils, labeled Coil A and Coil B, have declared duty percentages and are designed to be flow-proof, ensuring reliable operation. The fan wall comprises modular fans sharing a common air path, which adds to flexibility in managing airflow. It's important to state conditions explicitly, whether we are running in normal split mode, experiencing loss of capacity in path A or path B, and how fan power compensation is applied. This helps us predict the resulting rack inlet conditions accurately and maintain optimal cooling performance. In this module, we're focusing on Hall Airside Cooling and specifically on calculating the fan wall unit, or FWU requirements. The key takeaway here is that modular redundancy isn't just about having extra units. It's crucial to check both airflow and fan power to ensure reliable operation. Starting with the example assumptions. The zone duty is 3.15 megawatts with a temperature difference, or delta T, of 12 Kelvin. Each FWU provides 320 kilowatts of net cooling power and moves 90,000 cubic meters per hour of air, with 10 fans per unit. First, we calculate the zone airflow by dividing the thermal load by the product of air density, specific heat capacity, and delta T, resulting in 783,000 cubic meters per hour. Next, the duty count is determined by taking the maximum between the number of units needed based on cooling capacity and the number based on airflow, which gives us 10 duty FWUs. For water flow, we divide the cooling load by the product of water's specific heat and temperature difference, leading to about 7.54 liters per second per duty FWU. Then, considering one fan loss, the remaining fans must speed up to approximately 111% of their normal speed, increasing wall fan power to 123.5% to maintain airflow. This highlights why each fan motor and drive must be verified to handle these conditions. As a result, we select 10 duty units plus 1 standby, totaling 11 FWUs installed, ensuring that the system can compensate for a fan failure without losing performance. Finally, it's essential to verify fan curves, system resistance, zone air distribution, motor kilowatt ratings, acoustic limits, coil capacities, and conduct representative fan loss tests to confirm system robustness. In this module, we focus on the airside cooling of data halls, specifically the DOAS and dehumidifier working principle, where one authority controls the dew point. This means the process and regeneration air streams remain physically separate. The CRAH or fan wall units handle the sensible cooling load, while the MAU or DOAS manages moisture control. For process air, the sequence involves filtering outside air, pre-cooling it, passing it through a rotor or cooling coil, and then post-cooling or reheating before supply. On the regeneration side, it's crucial to use an appropriately valued heat source and maintain a separate exhaust path, steering clear of unverified claims, like zero-energy reheat. Control is based on supply or room dew point and humidity ratio, not just relative humidity, to avoid conflicting operations like simultaneous humidification and dehumidification. Finally, acceptance proof involves verifying airflow, humidity ratios at entry and exit, supply temperature, alarms, fallback procedures, and ensuring no opposing controls are active. This slide focuses on the critical aspects of selecting DOAS and dehumidifier equipment for Hall Airside Cooling. First, the latent equipment selection depends on the outside air mass flow and the humidity ratio reduction needed to maintain proper moisture control. Moisture duty is calculated using design outdoor humidity ratio and the required supply humidity ratio, making allowances for leakage, exhaust replacement, and door openings. It's also essential to confirm how condensate or rotor removal performs at the declared entering conditions. Next, filtration and corrosion protection are tailored to the outdoor air quality. Filter classes are chosen based on actual requirements, and gas phase media selection depends on measured contaminants or corrosion risks, rather than generic assumptions. Energy considerations include calculating pre-cooling, latent, post-cooling, and reheat or regeneration energy demands. Recovered heat is only valuable if temperature, availability, and system topology are verified. Finally, failure response protocols must ensure safe ventilation is maintained or the outside air path is closed according to the approved risk strategy. Alarms for dew point loss are crucial, as is isolating any failed components like heaters, rotors, or coils to prevent conflicting system commands. A project criterion such as maintaining a fixed plus 12.5 Pascal pressure, G1 corrosion class, or less than 60-second recovery is only applied when backed by sound design basis and evidence. This comprehensive approach ensures reliable and efficient airside cooling for data centers. This slide focuses on the DOAS and dehumidifier calculation for moisture removal and total coil duty in airside cooling for a data hall. Using a Jakarta example with explicit project weather and supply state assumptions, we calculate the dry air flow rate by multiplying the volume flow rate by the dry air density, which comes out to 8.63 kilograms per second. Next, moisture removal is determined by considering the difference between outside and supply humidity ratios, resulting in 326 kilograms of moisture removed per hour. The total cooling load on the coil is about 400 kilowatts, calculated from the difference in enthalpy between the inlet and outlet air states. Additionally, reheating requires approximately 61 kilowatts to reach the desired supply air temperature. Based on these numbers, the system should select a net coil capacity of at least 430 kilowatts and be capable of removing 350 kilograms per hour of moisture. It's essential to add redundancy and verify factors like weather percentiles, infiltration, coil and rotor performance, condensate handling, and sensor accuracy to ensure reliable operation. In this module, we focus on data hall airside cooling using the CRAC DX architecture, which is a self-contained room cooling system that rejects heat externally. The cooling capacity here depends on several factors like the entering air conditions, outdoor ambient temperature, the refrigerant circuit, fan-generated heat, and the rating method declared. Inside the data hall, the indoor unit includes essential components like the filter, evaporator, EC fan, controller, and condensate system. It's important to use the net sensible capacity measured at actual data hall conditions for accurate performance. Moving to the refrigerant circuit, it consists of the compressor, expansion device, piping, refrigerant charge, and leak safety mechanisms. Note that circuits should be independent only when the complete refrigerant path is fully separated. The outdoor condenser is sized based on the approved ambient design point and must consider recirculation conditions. It's also critical to maintain proper access for maintenance and ensure failure separation for reliability. Finally, ASHRAE Standard 127 provides a uniform rating test method for these systems, but every project must still declare the specific selection and site derating conditions to reflect actual operating environments. In this module, we focus on data hall airside cooling within the Data Center MVAC system, emphasizing CRAC DX redundancy, efficiency, and refrigerant safety. Uptime and TIA standards establish resilience outcomes, while ASHRAE 127 supports system rating, and ASHRAE 15 and 34 govern refrigerant safety and classification. When considering capacity and redundancy, it's important to count duty units based on net sensible capacity under site conditions, and map indoor units, compressor circuits, condensers, power, and controls to potential maintenance and fault scenarios. Remember, not every 2N arrangement meets universal TIA requirements. For ambient derate, always use approved climatic design data alongside manufacturer performance tables, and check factors like condenser recirculation, fouling, and high ambient control stability to maintain optimal operation. Regarding refrigerant safety, apply ASHRAE 15 to 2024 and 34 to 2024 standards for occupancy, charge limits, detection, ventilation, and safety classification. It's also crucial to note that the popular single GWP less than 700 rule is not mandated by ASHRAE 15. In control and power considerations, clearly defined strategies such as compressor anti-cycle, fast restart, and inrush current management. Additionally, ensure generator and UPS compatibility is validated through thorough electrical studies and integrated testing. Finally, the refrigerant choice must satisfy all applicable laws, safety classifications, equipment availability, serviceability, and align with your long-term life cycle decarbonization strategy. This holistic approach ensures a reliable, safe, and efficient cooling system for the data hall environment. On this slide, we're focusing on the CRAC DX calculation for data hall airside cooling. The key here is to determine the net unit count, electrical demand, and heat rejection based on ASHRAE 127 rating conditions with manufacturer site ambient corrections. Starting with our example assumptions. The hall duty is 1.20 megawatts, multiplied by a design factor of 1.10, giving us a design duty of 132 megawatts. Next, we calculate the duty count by dividing this design duty by the unit net sensible heat of 150 kilowatts, which results in 9 CRAC units required. For electrical input, we multiply those 9 units by 48 kilowatts per unit, totaling 432 kilowatts of power at rating. Then, for heat rejection, we add the sensible cooling and the electrical input per unit and multiply by 9 units, coming to approximately 1.782 megawatts. The recommendation is to select 10 units for an N+1 configuration to ensure redundancy, with the condenser system needing to handle at least 1.782 megawatts when 9 units are operating. Finally, it's critical to verify factors such as net versus gross capacity, sensible heat ratio, fan heat, piping derates, outdoor design conditions, refrigerant charge safety, and restart and generator step load capabilities. This thorough approach ensures a reliable and efficient cooling system design. In this module, we focus on Data Hall Airside Cooling, starting with the MU-DX system, which controls outside air, pressure, and moisture. But importantly, it does not manage the data hall's sensible load. The supply airflow is determined based on exhaust, leakage, and door allowances. After this airflow is set, the thermal equipment is selected by analyzing the enthalpy change from outside air to supply air. A critical concept here is the pressure cascade. We define the project pressure target across the actual clean boundary, typically aiming for a positive pressure between 5 and 15 pascals. However, it's essential to verify this target considering door force, leakage, and any smoke control system interactions to ensure proper operation. Moisture control is managed by regulating the supply or room dew point through a single coordinated authority, avoiding conflicts like CRAH units overcooling while the MU reheats or dehumidifies simultaneously. For air quality and interlocks, filtration is guided by outdoor air risk and local codes, while smoke, fire, and hazardous outdoor air responses follow approved life safety cause and effect systems. Finally, note that no single standard such as Uptime, TIA, or ASHRAE universally mandates specific pressure values, wall display requirements, UPS duration, or fast restart times, so these must be determined based on project-specific needs. In this module, we focus on the Data Hall Airside Cooling within the Data Center MVAC system. The key component here is the Makeup Air Unit, or MAU, which requires careful selection of filtration, humidity control, smoke detection, and refrigerant interlocks. It's critical that the unit acts as a boundary control system and fails safely to prevent any uncontrolled infiltration. Maintaining proper air balance involves replacing exhaust air plus accounting for envelope leakage and door allowances, while continuously measuring outside, supply, and exhaust air, along with trending room differential pressure. Filtration must be chosen based on outdoor air quality and equipment sensitivity, using both particulate and gas phase filters, and designed for safe changeout without compromising system resilience. Smoke detection and outdoor hazard systems need to integrate intake dampers, fire signals, generator exhaust, and air quality alarms, with life safety overrides taking precedence over comfort or pressure demands. For refrigerant safety, refrigerant detection and ventilation must comply with ASHRAE standards and local codes. Ensuring the system only restores operation once the cause is cleared, airflow is safe, and dew point is controlled. Ultimately, the MU is only complete when all components, outside air intake, fan, coil, dampers, drainage, sensors, power, and cause and effect controls, are fully integrated and tested as a single system. On this slide, we're focused on the airside cooling calculations for the Data Hall's Makeup Air Unit, or MU. First, we address leakage airflow, which depends on the effective area, discharge coefficient, and pressure difference. Here, those values give us a leakage flow of 1.73 cubic meters per second. Next, we calculate the total MAU airflow by adding the leakage, exhaust, and door allowance flows, then applying a safety factor, resulting in a required airflow of 4.05 cubic meters per second. Moving on to moisture load, we multiply the adjusted airflow by the moisture content to estimate moisture removal at about 176 kilograms per hour. Finally, total cooling load is derived from the airflow and temperature difference between outside air and supply air, giving us roughly 216 kilowatts of cooling capacity needed. Based on these results, the recommended MEU size is 4.1 cubic meters per second airflow with at least 240 kilowatts of net cooling capacity, typically installed as a 2 by 100% duty and standby setup for reliability. It's crucial to verify all these assumptions in the field, checking leakage, door operation, exhaust, weather, filters, and safety systems before finalizing the unit selection. This slide focuses on the standards alignment for Data Hall Airside Cooling, highlighting objectives, infrastructure, and engineering performance. It's crucial to use each standard for its intended purpose and avoid turning design preferences into universal rules. Starting with the Uptime Institute, it defines Tier 3 and Tier 4 topologies, emphasizing concurrently maintainable components and fault-tolerant, continuous cooling environments. This is performance-based, so there's no universal mandate on specific equipment restart times or UPS configurations. Next, ANSI/TIA 942C, updated in May 2024, covers key aspects of data center infrastructure such as site selection, architecture, electrical and mechanical systems, fire safety, telecom, and security. Remember, always refer to the license standard for exact rated 1 to rated 4 requirements and documentation, and don't attribute unverified values or metrics to the TIA standard. Finally, ASHRAE standards address thermal conditions, energy performance, equipment ratings, refrigerant safety, and climatic data relevant to data centers. Compliance with all these standards is shown through detailed criteria, calculations, drawings, operating sequences, and preserved test evidence to ensure proper engineering and operational performance. This slide focuses on the uptime implications for airside cooling within data centers, specifically referring to Tier 3 and Tier 4 performance objectives. Tier 3, known as concurrently maintainable, means that every capacity component and distribution path can be taken offline for planned maintenance without affecting operations. However, during maintenance, the site remains vulnerable to equipment failure or operator error. Tier 4, on the other hand, is fault-tolerant, ensuring that an individual equipment failure or distribution path interruption does not impact operations at all. It also incorporates concurrent maintainability and uses continuous cooling to maintain a stable environment, even through mechanical restarts. When designing these systems, it's critical to map all components, like units, fans, coils, piping, power, controls, and sensors, to specific events and avoid shared components that could undermine reliability. Evidence of compliance includes design documents, constructed arrangements, performance tests, and operational procedures that demonstrate sustained readiness. Remember, the tier classification evaluates the entire site topology and actual outcomes, not just isolated equipment or universal response times. This slide covers some critical points from Module 10 on Data Hall Airside Cooling, focusing on the ANSI/TIA 942C standard and its implications. First, it's important to note that Revision C is the latest version, and the exact requirements need to be referenced from the licensed standard and aligned with the specific project certification scope. Starting with physical infrastructure, ANSI/TIA 942C helps coordinate key elements like architectural, electrical, mechanical, fire safety, telecom, and security systems. It's essential to apply the rated level requirements comprehensively across all systems and distribution paths to ensure reliability. Moving to mechanical design, the standard emphasizes documenting capacity, redundancy, and the routing of piping and refrigerants, while also ensuring environmental controls, monitoring, and maintainability are in place. Coordination of equipment location is vital to manage leak risks and provide safe access for maintenance. For controls and monitoring, the focus is on defining sensors, alarms, command and feedback systems, along with ensuring network resilience and local fallback mechanisms based on the project's design basis. Keep in mind, the TIA standard does not mandate a specific protocol, ring recovery time, or wall display, leaving some flexibility here. Certification evidence is crucial, including maintaining a clause register, detailed drawings, schedules, calculations, and cause and effect analysis. Commissioning results and facility verification play a key role in demonstrating conformity. Finally, use TIA 942C primarily to coordinate infrastructure components, but rely on ASHRAE guidelines and specific project engineering criteria for thermal performance, rating, and safety values. This approach ensures a balanced and comprehensive design. In Module 10, we focus on Data Hall Airside Cooling, framed within the Data Center MVAC System Advanced Training. The key to understanding this section lies in the ASHRAE thermal, energy, rating, and safety framework, where each reference plays a distinct role. For thermal guidance, TC 9.9 directs us to control and verify conditions right at the IT air inlet, not the average room return temperature, maintaining a recommended temperature range between 18 and 27 degrees Celsius and considering humidity constraints. Energy compliance is covered by Standard 90.4 to 2025, which sets the energy performance expectations while keeping reliability and life safety as top priorities. Standard 127-2020 ensures uniform test requirements for cooling equipment ratings, urging consistency in declared test conditions and net capacity. Then Standards 15, 34, and 169 address refrigerant safety, classification, concentration limits, and climatic data essential for outdoor design conditions. Finally, an important training correction to note. There's no universal 5-degree, 15-minute ramp or guaranteed metrics like GWP below 700 or SHR above 0.95 without a specific clause or project basis. This layered framework ensures we approach data center cooling with precision and safety in mind. Now let's dive into commissioning levels for the Data Hall Airside Cooling System, spanning from L1 to L5. These levels are designed to progressively prove design intent while maintaining clear traceability from individual component evidence all the way to overall room performance. At L1, we start with the design review, looking closely at criteria, calculations, system topology, sequences, and acceptance values. We also verify standards compliance and establish the instrument plan. Moving to L2, factory testing ensures declared capacities, control logic, alarms, and restart behaviors are documented and tied back to specific serial numbers and configurations. When we reach L3, installation checks cover equipment, piping, power, sensors, and labeling with thorough point-to-point verification and calibration. L4 focuses on functional testing under various scenarios, such as normal operation, load changes, standby modes, failure conditions, and system recoveries, backed by command and feedback data. Finally, L5 is the integrated phase where the system is tested under representative loads and source transfers, including equipment failures and room recovery, ensuring cross-system coordination with life safety. The process culminates at the handover gate, where all deviations are resolved or accepted with risk ownership. Baseline trends are documented, and standard operating, maintenance, and emergency procedures plus training are complete. In this module, we focus on integrated testing to prove the real airflow path under disturbance in Data Hall Airside Cooling. The test process is carefully controlled by prerequisites, safety measures, calibrated instruments, and clear abort criteria to ensure accuracy and safety. First, we prepare by following an approved script, setting load profiles, mapping instruments, defining switching methods, and establishing communication and recovery plans. Next, we establish a baseline by measuring stable rack inlet conditions, airflow, pressure, dew point, unit state, and available capacity. Then, we introduce a controlled disturbance by injecting an approved loss event, such as a fan or power failure, one at a time. We observe the system's response by recording commands, feedback, physical and thermal changes, alarms, and operator actions. Finally, we recover by following the approved sequence to restore the system, proving that the margin, stable state, and evidence are retained. This process allows us to witness the complete chain from trigger to verified restoration, ensuring the cooling system performs reliably under real-world conditions. This module covers the acceptance criteria and evidence pack for Data Hall Airside Cooling Systems. Each criterion clearly states where it applies, how it's measured, and the type of evidence required to prove compliance. Starting with the rack inlet, all mapped inlets must fall within the approved project band and equipment class, ensuring there are no unacceptable transients during maintenance, faults, or restoration. We verify this with calibrated maps and synchronized trend data. Next, airflow and pressure must closely follow IT demand while keeping bypass and recirculation within limits. Room and containment pressure should remain stable within the project band, without causing excessive door force. We confirm this using traverse measurements, differential pressure, and airflow balance data. On the heat balance side, the air side and water side or refrigerant duty need to reconcile within stated uncertainties. Available capacity must meet the tested state, supported by flow readings, temperature data, kilowatt measurements, and vendor rating information. For control, failure, and restore functions, the commanded sequences, interlocks, fallback modes, and alarms are validated to operate as approved. Importantly, there should be no unsafe auto reset, and restoration must only occur with explicit permission. Evidence for this includes cause and effect diagrams, event logs, trend charts, and signed test sheets. Lastly, every result must record uncertainty factors like sensor location, test load, ambient and plant conditions, system configuration, and any unresolved deviations to provide a thorough and transparent acceptance package. In this module, we focus on Data Hall Airside Cooling and explore the critical relationship between air path defects and IT thermal margin failures. Understanding how airflow issues translate directly into thermal risks is essential for maintaining data center performance. We use failure mode and effects analysis, or FMEA, to rank potential failures based on their physical consequences, how easily they can be detected, and how much time we have before the rack inlet temperature exceeds safe limits. For example, a fan or power loss results in reduced airflow and static pressure, while filter blockage or coil fouling degrades coil performance and cooling capacity. Valve or refrigerant circuit issues cause heat redistribution through bypass or recirculation, and sensor or controller failures lead to unstable control behavior. Detecting these faults involves monitoring key parameters like rack inlet temperature trends, fan power and flow rates, and filter pressure drops. Effective response means isolating faults promptly, protecting IT equipment, preserving evidence, and restoring systems with authorization. Importantly, the control mode must always reflect the physical state, whether manual, local, networked, or fallback, ensuring reliable operation throughout. This integrated approach helps us proactively manage thermal risks and keep our data center running smoothly. When troubleshooting Data Hall Airside Cooling, it's crucial to localize any imbalance before changing settings to avoid unintended consequences. The process involves moving systematically from the protected load, starting with confirming rack inlet conditions and activating reserve capacity if thermal margins drop. Then validating sensor accuracy and timing against calibrated references. Next, we trace the airflow by checking IT demand, containment effectiveness, and potential obstructions including fan and filter conditions. After that, we trace the cooling side, verifying valve operations, flow rates, temperature differentials, and overall coil and plant conditions. Finally, we make one controlled correction at a time, retesting to ensure room performance and system resilience are fully restored. Always remember the hold point. Stop immediately if there's any doubt about rack thermal margin, personnel safety, containment integrity, or control authority. When we encounter a high rack inlet temperature, the standard operating procedure is critical to follow carefully. First, confirm the issue by identifying the specific affected rack, height, or zone, and validate it with independent temperature measurement and trend analysis. Then, protect the affected equipment by activating any available reserve units or fans, or initiating an approved IT response before the thermal margin is compromised. Next, check the air distribution thoroughly. Inspect doors, blanking panels, containment systems, and ensure there are no obstructions in tiles, grills, or fan airflow. After that, verify the cooling system's performance by examining valve flow, temperature differentials, DX circuits, coil and filter conditions, supply temperatures, and the state of the plant and ambient environment. Finally, restore normal operation by correcting the root cause, stabilizing the temperature profile, recovering redundancy, and retaining all evidence before closing out the issue. It's important to avoid shortcuts such as blind set point reductions, uncontrolled fan speed increases, opening permanent bypasses, or masking alarms, as these can lead to further problems. Maintenance is crucial for preserving airflow, heat transfer performance, and ensuring sensor accuracy. Before returning a system to service, you must complete safe isolation, thorough cleaning, calibration, functional testing, and provide representative proof that everything is working correctly. On the mechanical side, this includes checking fans and motors, filters and coils, valves and strainers, drains and condensate systems, and refrigerant integrity. For the air path, Ensure that doors, blanking panels, containment seals, grills, plenums, and any potential obstructions are all in proper condition. Sensors and controls also need attention. Verify their location, calibration, plausibility, network connectivity, local fallback options, alarms, and retained trend data. Finally, the return to service gate requires a correct lineup with no leaks, serviceable filters, coils, and fans, valid instrumentation, and proven capacity along with failure reserves. In an emergency operating response for Data Hall Airside Cooling, the first priority is always life safety and thermal stabilization. We must preserve evidence and restore systems deliberately to prevent further issues. The initial step is to start standby systems, or reduce the load by using approved capacity. If the thermal margin keeps falling, apply the approved IT workload adjustments or load shed responses, and escalate the situation to the incident authority. Next, open only approved alternate paths using engineered valves, dampers, or bypass paths. It's crucial to confirm that these actions don't compromise smoke control, leak detection, or the overall topology protection. Maintaining the dew point and pressure is vital. Keep the moisture boundary safe and avoid conflicting commands. Control infiltration, monitor door conditions, and verify room pressure continuously. Finally, recovery must follow the approved sequence once the cause is resolved. Document every detail: triggers, operator actions, room response, alarms, and recovery steps. Remember, no permanent manual overrides, alarm masks, or containment breaches may remain after stabilization. In this practical lab, we focus on balancing airflow within the data hall and racks, which is crucial for effective airside cooling. We start by calculating the net airflow required based on key assumptions, including an IT-sensible load of 3.8 megawatts, a temperature difference of 11 Kelvin, air density, and specific heat capacity. Using these values, we determine the net airflow to be 286.2 cubic meters per second. Next, we account for an 8% bypass allowance, adjusting the supply airflow to 311.1 cubic meters per second. This helps us estimate the number of duty airflow modules needed, which rounds up to 22 units to handle this supply volume. Field closure is then addressed by comparing the supply airflow, IT demand, and bypass volume, using a formula that incorporates measurement uncertainties to define a pass band. The lab output includes creating a rack-level airflow allocation map, predicting bypass volumes, establishing the duty module lineup, and planning field sensor traverses. Importantly, the calculated airflow values are only considered valid when they reconcile with actual measured supply distribution, rack intake demands, and containment conditions, ensuring a true balance is achieved. In this practical lab, we focus on designing and validating the rack inlet sensor plan for Data Hall Airside Cooling. First, it's essential to map all equipment intakes accurately, ensuring we have distributed sensors, calibrated reference instruments, and reliable time series data to support our analysis. We pay close attention to sensor location, covering the top, middle, and bottom of critical and typical racks to get a comprehensive temperature profile. Accuracy is crucial here. Knowing the sensor's range, uncertainty, and calibration status ensures data reliability. Next, we consider control aspects by identifying which sensors actually drive demand response and verifying the plausibility of the readings. Trend analysis involves synchronizing timestamps and setting appropriate sample intervals to detect meaningful patterns. Finally, acceptance criteria require that each sensor is properly positioned, calibrated, and monitored over time. We must witness all necessary racks and sensor heights and perform a risk assessment for any measurement gaps, accounting for both steady state and transient conditions, as well as potential failure states. This thorough approach ensures our cooling strategies are based on accurate, actionable data. In this practical lab, we focus on the fan failure heat load test and the stable recovery process. First, we start with a baseline, capturing a representative heat load, monitoring a stable rack map, fan power and speed, along with containment and available reserve capacity. Then, during the trigger step, we remove one approved fan or module, carefully recording the event time and command and feedback status. Next, we observe the response where the remaining fans compensate and standby capacity activates only as designed, while alarms warn us of reduced resilience. Following that, we verify that the rack inlet temperature stays within approved transient limits, and that motor power, speed, and distribution remain within set parameters. Finally, we restore the system safely by removing any overrides, recovering redundancy, and keeping documented evidence. The key to passing this test is maintaining a protected rack inlet and verifying available cooling capacity, not just ensuring the controller runs without alarms. Now, let's focus on handover evidence and operating readiness for the Data Hall Airside Cooling System. The asset is considered ready only when all technical, procedural, and competency evidence is fully completed. Starting with design, this includes having an approved design basis and clause register, finalized calculations, selections, topology, and a clear control narrative, along with as-built drawings and equipment schedules. Moving to installation and commissioning, it's crucial to have comprehensive factory and site records, calibration and point-to-point testing, L4 and L5 scripts, raw trend data, and closed deviations documented. For operations, the team needs to have standard operating procedures, maintenance and alarm response plans, baseline sensor and thermal maps, spare parts, and trained, competent staff. The key handover gate is when the operating team can confidently explain the design intent, handle any failures, and retrieve all necessary evidence independently, without relying on the designer. In this module, we focus on Data Hall Airside Cooling within Data Center MVAC systems. Learners are expected to demonstrate engineering judgment beyond simple recall. You'll need to trace heat, air, water, refrigerant, and moisture paths, and understand why relying on room average measurements is not enough. You will also calculate key parameters such as airflow, water flow, moisture duty, fan loss power, and pressure makeup. When it comes to design, you'll select system architecture, determine redundancy, map sensors, and define control authority along with failure response strategies. Execution involves building safe control scripts, establishing abort criteria, and operating high rack inlet standard operating procedures. You will also evaluate system performance by interpreting trends, heat balance, and failure mode evidence, distinguishing root causes from control symptoms. Finally, diagnosis skills will allow you to pinpoint defects in air, cooling, or sensing paths, correct a controlled variable, and demonstrate recovery effectively. This comprehensive competency assessment ensures you apply both knowledge and practical skills in real-world scenarios. As we conclude Module 10 on Data Hall Airside Cooling, it's essential to remember that compliance with licensed standards ensures both safety and performance. Key references include the Uptime Institute Tier Standard, which guides topology and tier certification, alongside the ANSI/TIA 942C and ASHRAE thermal guidelines tailored for data processing environments. Engineering standards like ANSI/ASHRAE 90.4 to 2025 and 127.2020 provide energy and cooling equipment performance criteria, while the ASHRAE safety standards govern refrigerant use and climate data. For project execution, comprehensive documentation such as design basis, load models, control narratives, and commissioning scripts is critical. Always measure at the IT inlet, separate sensible and moisture duties, and verify both capacity and failure response through documented evidence. Standards set the objectives, but it's the project design basis that turns these requirements into clear, measurable acceptance criteria, ensuring a reliable and efficient data center cooling system. As we close out Module 10 on Data Hall Airside Cooling, the key takeaway is that cooling is only truly effective at the equipment intake. A successful cooling system relies on several critical factors working together seamlessly. First, we must measure rack inlet temperature, dew point, airflow, and pressure right at the physical decision point to understand exactly what's happening. Next, separating containment, ventilation, pressurization, and sensible cooling responsibilities ensures each function is managed optimally. Then, it's vital to reconcile the airside conditions with waterside or refrigerant cooling capacity across all operating states. When issues arise, a robust fault response and local fallback plan must restore normal operation quickly and safely. Finally, proving system performance through representative load conditions, calibrated instruments, synchronized data trends, and signed evidence gives us the confidence that everything is working as intended. With these 5 steps, measure, separate, reconcile, restore, and prove, we build systems that deliver reliable, efficient cooling. Next up, we'll explore Module 11, focusing on station point and direct-to-chip liquid cooling.